Well, hello everyone. We are looking at our second lesson within this hydrocarbons kind of section for the chemistry today. So with this one, we're going to be looking at how hydrocarbons, how their properties, so physical properties, things like boiling point, flammability, and viscosity, which is the thickness of the liquid, how they change as the length of the hydrocarbon chain changes. What we're then going to do is we'll have a little bit of a think about how that will affect particularly their uses as a fuel. So first job is, I've got this diagram here which is our fractionating column and our separations, and we can see that there are some values within this diagram. So since we're going to be looking at trends and patterns today, I'd like you to have a look at the data here, pause the video and think about what the trends and patterns are that you can actually identify. So hopefully you will have noticed that as you move up the fractionating column, one of the things that you will see is that the boiling point actually decreases. So that boiling point gets lower as we go higher up the fractionating column. And we know that's true because we were looking at fractional distillation last lesson, and we know that there's a temperature gradient within the column, and that the column itself is hotter at the bottom and cooler up at the top. Right. So here we have fractionating column represented in a different way, and so we can see that temperature gradient shown really nicely. We can see we've got our crude oil vapor going in here, and we can see the different fractions that are coming out. And so I just at this point in time want you to think a little bit about the properties of these molecules in general. I'm going to move into explaining these a little bit more. So down at the bottom, our bitumen or heavy fuel oil, we consider these large molecules. And so that means that they've got a high boiling point, which we know because the column is hotter here, and so they condense at these high temperatures. What that therefore means is they're not very volatile. So volatile is all about how easily this substance turns into a gas. So bitumen doesn't turn easily into a gas, which makes sense. It's a really thick liquid. Which brings us to this point. It doesn't flow easily. It's viscous. And also, it does not ignite easily, so it's not easy to set fire to. So we know that setting fire to roads is a difficult thing. Whereas if we go up to the top where we have our liquefied petroleum gases, so LPG, so the kind of gas that you've got in your gas cooker, those things have low boiling points, which means that they're very volatile, so they turn into gases really easily. We know they're a gas, they come into our room, into our houses as a gas. It means they flow really easily, and because they turn to a gas really easily, we can set fire to them really easily. They ignite easily, they're very flammable. Now, one of the things is that these are the fractions that you need to know, and so there's a little way to remember this, so a little acronym for you. And so this one is lazy penguins keep drinking hot beverages. So I know that some of you appreciate a good acronym in order to be able to remember your way around these things. Another table for you here. So here we have the alkanes, which you remember because they've got their ANE ending, and we can see the formula for them. So we can see we've got 1 carbon here going up to 9 carbons in non-ane. So Me, remember, stands for 1 carbon, eth is 2, pro is 3, but is 4, pentagon, 5 carbons, hex 6, hept 7, oct is 8, non is 9, and of course dec is 10. And then ane tells us that they are all in the ane family, the alkane family. So moving down, we can see the relative atomic mass, and we can see the boiling points here, ranging from -161 to 151 degrees C. What I'd like you to do is, again, pause the video at this point, and I want you to consider what the trends that you can see in the data here are. So the first thing that I would want you to pick up on is the fact that the boiling point increases as we go down. So these numbers initially become less negative and then they become more strongly positive, which means the boiling point gets bigger. And we can make a link between that boiling point and the change in the molecule size. So we can see that the molecules get larger, their mass gets larger, and so as the molecule size increases, we have boiling point increases. Now that's important. We need to hold that in our heads for a little while because we're going to explain that a bit later on. So properties of hydrocarbons, you need to be able to focus on three properties of hydrocarbons. You need to explain what the trend, or identify the trend in these properties, and then explain the trend in these properties. So our first thing that we need to take from this is that the properties of hydrocarbons depend on the size of the molecules that make them up, and we saw that in the previous table. So we're going to take that a little bit further as we move through. There are three properties which you need to be able to identify the trend in and to be able to explain the trend in. So the first one is the boiling point. We've just had a look at that. So you could see that the boiling point increases with molecule size. The second one is the viscosity. So viscosity is a measure of how thick the liquid is. So we can see it represented in this diagram here. We can see that this liquid here is pouring relatively easily, whereas this liquid here is much thicker. It's taking a much longer time to be able to pour. So we will call this liquid viscous, and we could use the term that this is less viscous, or we could say this liquid is runny. So tomato sauce, honey in your house, brown sauce, all very viscous liquids, whereas milk is not a very viscous liquid. The second property, or final property that we want to consider is flammability. So how easily does a compound actually set on fire? How easy is it to ignite? And along with that goes generally how easily it burns, and so how clean it burns as well. So we've already had a bit of a chat about what viscosity is, and again we can see a thick viscous liquid here. So if we extend this into hydrocarbon fuels, some hydrocarbon fuels are thin and runny, whereas others are thick and sticky. The thickness of the liquid, as we said, is called viscosity, and if we're going to talk about some examples within our fraction distillation fractions, then we could say that the bitumen which is produced is very viscous, it's very thick, it's the tar that we use on roads, so it cannot be poured easily, whereas petrol has a much lower viscosity and so pours really easily. So the really important principle here, and we'll summarise all of this towards the end, is that the longer the hydrocarbon chain is in a fuel, the more viscous that fuel will be. We're going to explain that now. So when we are talking about fuels that have large hydrocarbon molecules, long hydrocarbon molecules, we say that they're more viscous. Now there are two reasons for that. The first one is represented in this diagram. So over here on the left hand side we can see that we've got butane, C4H10, and we can see that there are these blue dots in between them. So these blue dots are the intermolecular forces, and so we can see that between our butane there are only a few opportunities for intermolecular forces to form, and so they're held together relatively weakly. Whereas if we jump over to this molecule here, C20H42, this is a much longer chain. So you can see that there are 20 carbons in that chain, and therefore those intermolecular forces where they form, remember they're weak, but the point is that between this molecule, instead of having 1 or 2 between each molecule, we've got 5 or 6, and so those intermolecular forces are much stronger. If they're much stronger, we have to add them all together, and so it takes more energy to be able to break them apart, and so what it means is that these liquids will be more viscous, they'll be harder to pour. So as molecules get bigger, the intermolecular forces get bigger, so it takes more energy to separate the molecules, and so we can say that the viscosity is higher. This also explains the trend in boiling point and the trend in flammability as well. So there is a second reason as well why we can talk about that large hydrocarbons are more viscous than small hydrocarbons, and that ties into how easily the molecules actually entangle. So we can see here that with this long chain molecule that the individual molecules have got tangled up. It's like a big bowl of spaghetti, and they're all tied together. Whereas over here, these smaller chain molecules have got less opportunities to get entangled, and so they're easier to separate, and it takes much less energy in order to separate them. This explanation is less important. The really important one is the idea of intermolecular forces. So, boiling point of hydrocarbons. Long chain hydrocarbons have stronger intermolecular forces, as we said, and of course they also become more easily entangled with each other. Therefore, it takes more energy to separate the longer chains, so we need to heat them up to a higher temperature in order to be able to separate out the individual molecules. If we have to heat them up to a higher temperature, that means that the boiling point will be higher, so it takes more energy to turn those substances into gas. So a secondary point that we want to think about here is that fuels that have a low boiling point, so we saw some of those fuels in that table right at the start had boiling points of 0 or below 0, they will be gases at room temperature, and so they evaporate really easily, and so we can describe those as being really volatile. Key point from this one is, as the length of the hydrocarbon chain increases, the boiling point increases. So as the length of the hydrocarbon chain increases, we've had an increase in viscosity and an increase in boiling point. Right, flammability is a little bit different in its pattern, and it links to the previous idea of volatility. So the first thing that we need to remember is that for our combustion triangle, we know that oxygen was one of the sides of that combustion triangle. So in order for fuel to burn, it's got to react with the oxygen in the air, and so in order to do that, it's got to evaporate and turn into a gas. So if a fuel is able to evaporate easily, then we know that the hydrocarbon chains that are in it must be quite short. And so we can describe that fuel as being volatile, as we've previously said. Therefore, it will mix with the air more easily, and so if it mixes with the air more easily, it will ignite and burn more easily. Therefore, we can describe those fuels with short chain hydrocarbons as volatile. It means that they will burn very easily, and so we can say that they are flammable. What this also means is that they will burn more cleanly, and so we get less soot given off and less smoke being given off. We get less black kind of smoke. So, key principle here is generally the smaller the molecules in a fuel, the more flammable it is. So, summary slide, you need to make sure that you write this down, is that in the principle that we've identified is that as we get a longer hydrocarbon chain, we get stronger intermolecular forces, and also the molecules become more entangled. If we have stronger intermolecular forces, therefore the hydrocarbon will require more energy to overcome the intermolecular forces that we find. So it will take more energy to separate that mixture of hydrocarbon molecules into individual molecules. So it takes more energy, for example, to turn it into a gas. What this therefore means is that longer chain hydrocarbons have higher boiling points, they are more viscous, and they will be less flammable as a result. Okay, so make sure you write down those 3 points, please. So, some questions just to finish up with where you were, or where we are. Pause the video now, answer these few questions, and having answered these few questions, we'll put the answers up. So how does the size of a hydrocarbon molecule affect the boiling point? Well, of course, a larger molecule means that we have a higher boiling point. How does it affect the flammability? Well, a large molecule will have a lower flammability, or a smaller molecule will have a higher flammability. How will it affect the viscosity? Well, a larger molecule will be more viscous. A hydrocarbon catches fire very easily. It's likely to have molecules with long hydrocarbon chains or short ones. Will it give off lots of black smoke when it burns? So if it catches fire very easily, that means it's very flammable. So therefore it must be a smaller molecule. So it's a short chain hydrocarbon. And will it give off lots of black smoke? Well, it's going to burn easily, it's going to burn cleanly, so it's going to give off little smoke when it burns. 2 more questions for you. So same principle. Pause the video, answer the questions, and then I'll go through the answers. So intermolecular forces are the force is found between molecules, and explain why the boiling point of a hydrocarbon increases with molecule size. Well, as the molecule gets larger, the intermolecular forces will get stronger and the molecules get entangled more easily. Therefore, it's going to take more energy to separate the molecules, and so the boiling point is higher. Right, thanks a lot. There are some other tasks for you to be getting on with, so crack on with those and submit me some work via sharing my homework, please. Thanks a lot.